So, welcome to this brief intermission. I want to talk to you about flow decomposition ahead of the applications that we are going to get into next. So, flow decomposition is just a nice way of thinking of a flow in terms of ST paths. And that's not a very unusual thing to do, considering we've been building up the flow by successively pushing flow through ST paths, more or less, even though we've done it in a residual graph which has some additional constructs. But still, it's a really useful way of thinking about flows, because once you go from thinking about flows as just numbers on edges which satisfy conservation and capacity constraints, to just thinking about them in terms of a linear combination of flows that are very special, which are basically flows along ST paths, then it's just easier to visualize them, it's easier to work with them. So it's really nice that every flow can in fact be thought of in this way. So you can probably see the statement of the theorem on your screen here, but let me actually walk you through it with an example instead. So remember that we had this flow on a flow network some time ago. So we have this edge from S to A being fully saturated, and the edge from A to B is also saturated. And so is the edge from A to C and C to D. And the edge from D to T is at half capacity. And the edge from B to T is at half capacity as well. I should probably point out that the numbers in blue are the flows and the numbers in red are the capacities. And for all the remaining edges here, there's basically no flow. So these are edges, the blue ones are the edges that are being avoided by the flow that we are looking at. So we have few edges that are saturated, few that are being avoided, and a few that are at half capacity. But if you look at the highlighted edges, you don't really see them necessarily as ST paths immediately. But notice that we can break this flow down into two different flows, which are both smaller in value. But when you sort of superimpose those two flows, then you recover this one. And by superimposing two flows, I simply mean that you pointwise add up the flow values at every edge. So you look at an edge and you look at how much flow is going through that edge in each of the individual flows that you're trying to add up. And the final flow through that edge is just the sum of those individual flows. So here is a first flow. It basically is a flow that pushes 5 units of flow along this ST path that's going on the top via A and B, and that's the first one that I want you to consider. And here's the other one. The other one is ST path that goes via A, C, D and ends up at T, of course. And here we are pushing a flow of 10 through this path. So if you have a ST path and you have active flow only going through the edges of that path, then notice that by conservation, all edges must actually be witnessing the same amount of flow, right? So that's the situation with both of these paths here. But now what does it mean to superimpose these flows? Well, the good thing is that for the most part, these two paths are disjoint except for the edge from S to A, which is present in both paths. So the final flow has on S to A flow of 15, which is the sum of 5 and 10 here, and everything else is just coming in from the individual paths. So you can pause and double check that this flow that we have here indeed can be thought of as the sum of the flow that's going through those two paths. And it turns out that you can actually do this for pretty much any flow. You can break it down this way, and you probably have some ideas yourself of how you might go about that. And let me just walk you through an informal discussion of a process that would help you decompose a flow into path flows. So basically what we are going to do is start at S, and because we're starting out with a flow which has, like, let's say some non-trivial value, because if it's a zero flow, well, there could be two reasons that it's a zero flow. It could just be that it's literally a zero flow. There is no flow going through any of the edges, in which case there's nothing to do. But on the other hand, it could be that this flow is actually what's called a circulation, which means that the entire flow actually cancels out. The net flow at S and T are also zero. Okay, so if the conservation property also holds at S and T, then that's a special kind of flow called a circulation. So for now, I'm going to be assuming that we are actually working with a flow that has a non-trivial value, that has a non-trivial positive value. It turns out that what I'm saying here can also be easily extended to circulations. And in fact, I'll make a comment about that at the very end, so we'll come back to it. But for now, let's just say we're working with a flow where S enjoys a net positive outgoing flow. Okay, now that implies already that there must be an edge that's going out of S that actually carries some flow. There is that's just from the definition. And let's say that, you know, one of those edges, at least, I mean, there's at least one, and let's fix the edge from S to some vertex V1. Now let's look at V1. V1's situation is that it has some incoming flow, and so there must be a compensating outgoing flow. Again, there could be additional incoming flow from other edges, but the point is, all that I want to hold on to is the fact that there must exist at least one edge that's going out of V1 which carries some flow, some non-negative flow. And mind you, I'm not insisting right now that these two flow values are the same. So you could have an incoming flow of 5 here and an outgoing flow of 3. And maybe for conservation, the excess flow goes out of some other edge. For all you know, there's more flow coming in from some other edge, and so on and so forth. So I don't really want to get into the nitty-gritties of the actual flow values here. All I care about is the fact that there is an edge going out of V1 to another vertex that I'm going to call V2 that actually carries some non-trivial flow. And I'm going to just keep extending this idea. I'm going to go to a vertex, realize that there's incoming flow, and by conservation there must be outgoing flow as well. And I'm going to keep going until one of two things happen. One thing that could happen is that you land at a vertex that you've actually seen before. So it's possible that this Vi is equal to some Vj for some j less than I, which basically means that, you know, you started at S, went around, and at some point you crossed your own path, right? And at this point, I don't even want to go further down. I want to stop here, because what I have found is actually a cycle in this graph, and I know that all of the edges on the cycle actually have non-trivial flow. Okay, so what I'm going to do at this point is basically eliminate this cycle. So I'm going to update the flow so that I basically get rid of the bottleneck flow on this cycle from all the individual edges. So for instance, let's say we have encountered this cycle, and the flow on these edges is, let's say, 3, 7, and 5. I'm going to have to update this to 0, 4, and 2. So I eliminated 3 units of flow from all the edges in the cycle, and 3 was the bottleneck flow on that cycle. So I'm going to call this process eliminating cycles, and we'll do this as often as is required. But if you don't get stuck in a cycle, if you don't loop back to a vertex that you've seen before, then the only other place that you can stop is actually T, because that's the only other vertex that has permission to violate the conservation constraint. Every other vertex will actually point you to another vertex that you can travel to. And if you're only seeing new vertices, then you must actually end up at T. Okay, so basically start at S and walk around along edges that have non-negative flow going through them, in fact strictly positive flow going through them, and one of two things will happen. Either you will see a vertex that you have seen before on your journey. The first time that happens, stop, look at the cycle, and clean up the flow on that cycle. Otherwise you end up at T, so you found one ST path, and then you modify the flow again in the same way. You take the bottleneck amount of flow, or well, look at the edge that has the least amount of flow going through it on that path, and update the flow so that that's the amount of flow that you subtract from every edge. So let's do an example of that as well. Let's say we start at S and go to the vertex W. From W we go to X, from X we go to Y, from Y to Z, and let's say that from Z we land up at T. And let's say that the flow that we see at each of these edges is like 1, 2, 3, 2, 1, something like this. Then the bottleneck flow, in this case, well, that's just the smallest amount of flow going through any of these edges on the path, is 1. So we are going to update the flow so that we shave off 1 unit of flow from each of these edges. So we are going to get 0, 1, 2, 1, 0. That's the purple numbers show the new flow through these edges. But what this actually means is that we are adding this path from S to T with a flow of 1 unit each to our decomposition. So that's one path that we have sort of peeled off from the flow, and we keep doing this. So at every iteration we are either peeling off a cycle or a path. Now if you're peeling off a cycle, just ignore it, okay? And if you're peeling off a path, add it to the decomposition. So this way you can actually break up a flow into component path flows, and this decomposition actually turns out to be quite useful. Now I did say that I'll make a comment about circulations. It turns out that if you're working with a flow that happens to be a circulation, which is to say that S and T have a net flow of 0, then this decomposition will only consist of cycles, and that's a nice exercise to think about. And if you don't have a circulation, because of what we just argued, you see that you can actually decompose a flow strictly into path flows, right? So all the other cycles that you encounter, basically the flow cancels out in those cycles. So that's something that you don't have to worry about, and you can see that any strictly positive flow can be thought of as a sum of paths. In fact, you could even say that each of those paths have a unit flow going through them, because for instance, if this was, instead of 1, 2, 3, 2, 1, let's say this was 10, 20, 30, 20, 10, then the updated flow would have been 0, 10, 20, 10, 0. So what we have shaved off is one path with a flow of 10 units through each edge, but you can think of that as further being decomposed into 10 paths of 1 unit of flow going through each of them, right? So that's the ultimate decomposition. You can, if your application calls for it and it's easier to view the flow that way, you can always assume that your flow consists of a bunch of ST paths that have unit flow going through them. So that would be the notion of a flow decomposition, which I promise will be handy in the segments that are coming up. And now we finally get to perhaps the most exciting bit, which is to see how we can apply the flow algorithm to solve many other problems. We will look at 3 examples. The first is tuple selection, which is basically an extension of the maximum matching problem, which you have perhaps already seen before. The next one is exam scheduling, which is a special case of the tuple selection problem, but it's just fun to see a concrete setting, which actually turns out to, again, be solvable by flows. And the last example we will see is an example centered around the IPL tournament, where we'll see that some matches have happened, and we will try to reason about whether there's any possible way that your favorite team can win. So all of that is coming up. I'll see you in the next video.